Hello and welcome to another Meyer Sound webinar. How's the transmission? Can everybody hear me? Can everybody see me? Hello, hello, hello. Anyone? Thank you. Thank you for confirming. We have super exciting content today, and that means that without further ado, let's go over the household notes as usual and then go to today's guest lecturer. So I'm going to share my screen and let's take it away. So today is going to be a very exciting journey where we get to learn about the evolution of system optimization. But before doing so, let's talk briefly about Zoom, because in front of you, you are expected to have a window, not unlike the one you see over here. If you would like to see who else is joining you today, all you have to do is click on the participants button, in which case a window opens up to the right side showing your fellow attendees. We encourage you to ask questions, but in order to do so in an organized fashion, we prefer you to use the raise hand feature. Notice that in the bottom right corner, there is a button called raise hand, and whenever you click that button, a blue hand icon pops up in the corner of my eye, informing me that you are about to ask a question. In order to ask the question itself, we would very much like you to use the chat feature. So whenever you click on the chat balloon icon, the right-hand window splits in half, bringing up another dialog. Notice that there's a field at the bottom where you can enter a message and then address the nation, that is to say everyone that is joining us today, or if you happen to see a family member, a fellow colleague, or a friend, you can also address that person in private. That pretty much concludes the household notes, and that means to those that are joining us as we're simulcasting to Facebook Live, to those that are joining us, welcome to you as well. The user community is growing at a steady pace, currently counting over 8,900 members and rising, so welcome to you as well. And that means that without further ado, I'm honored to introduce today's guest lecturer, our Director of System Optimization, none other than Bob McCarthy. Bob, are you with us?
Yes, sir, I'm here.
Excellent. Thank you for joining us. Hope you're doing well.
Yep.
Awesome. So whenever you're ready, we can start talking about what you have in mind for us today.
Well, I thought it would be interesting to go through what got us to where we are today. We all know what system optimization it is. It's a mature field at this point. It's something that people expect and as part of a sound systems journey. They expect it to be optimized before going through the process of mixing a show on it. And we've come a long way to get here. And there are some things that that you might not know from if you're young, if you're less than 200 years old. There's some pretty interesting things on the way to getting us here. So I thought I would do some history, but also keeping an eye on the how this evolution was done by people in real time with the vision of doing this work that we take for granted now, but how it wasn't always so easy and it wasn't always so clear what the path would be. Okay, so yes, in the beginning, you can recognize this. It's called our universe. It operates under an old-fashioned physics system, version 1.00. Release date was the Big Bang, and no updates are currently scheduled. So the thing I like about this is it means that things that we learn about physics and measurement, we get to keep with us. We don't have to relearn them. They won't be updating and changing. So in the beginning, there was, of course, the Big Bang. And after that Big Bang, somebody said, well, geez, how can we make that get louder? And that's why we're all in the speaker business. So let's take a journey back to the world of acoustic measurement. If you think that your current FFT analyzer is slow and you're waiting for answers and want it to speed up. Well, I want you to take a look at this analysis device, a collection of tuning forks. What are tuning forks for? Well, we know and think of them as an instrument to get your musical instrument in tune, but they were also basically, we had to find frequency, which we consider just a completely, we take it for granted that that's completely defined. Well, it wasn't always so. And the tuning fork was the tool to be able to find a frequency. So you made a tuning fork of a particular metal and density, and the purest of these things could do a single tone and vibrate only at that frequency. And these were used then to tune up a symphony and to make it so that the symphony in Stuttgart had the same pitch as the frequency as the symphony in Boston. Well, actually, they didn't. Just like our modern audio industry, nobody could agree on a standard even at that time. So the Stuttgart frequency was different than the Boston, who ran quite sharp, and on it goes. And we all think of A440 as completely standardized for everybody. Well, it wasn't, and that's a whole nother story we'll leave for someone else. But now tuning forks are good for a single frequency, and you can make them very precise. And here what you see is a thing called a clock fork, which was used to verify other tuning forks. And you can basically put them on a pendulum, and the pendulum runs a clock, and you're going to count the frequencies as if it's a like a carrier clock. Like we use clock frequencies now in our digital audio world, where you're using this clock and then you count down from there and multiply and divide to find the frequency of a particular fork that you're manufacturing. Helmholtz resonators, those are the beer bottles of audio engineering. The particular shape and volume of air creates a particular pitch that fits in there and resonates at that frequency. Again, it's another way to find a single frequency. What you see is the common thing here is we've got various ways to find one frequency, but be able to find a complex sound, such as made by any voice or any musical instrument, that gets much more difficult. This device here is called Koenig's phonautograph. And this was a recording device, and it's very interesting. What it's got now is it's got a two styluses. One stylus is attached to the diaphragm that is moved by your voice talking into this horn. So that wiggles the diaphragm. And then the second stylus is on the tuning fork. Why would you want a stylus on the tuning fork? Well, as you turn that wheel there by hand, it's going to scratch a piece of paper that somebody smoked the paper, so it's got a darkened surface on it, and the stylus scratches away that surface and essentially traces the waveform. Well, it traces two waveforms. One is the clock frequency, which comes from the tuning fork, and then the other is the frequencies vibrating from your voice or whatever musical instrument. So this way you can roll back unwind that piece of paper that's at the end of this event, and you've got two traces on there, a clock and the waveform. It's pretty amazing to think of sitting there and counting. That's the ultimate in analog counting, but that's the way you could tell what the frequencies were of my voice talking, or maybe a trumpet playing or something of that sort. Here you have a string vibrating, and they're photographing it. They put it in a dark room and run an exposure, and the white string against the black background you're able to see the excursion of that string. So people went through amazingly challenges to find out what these vibration forms were And this is a way you could see it visually and start to see here's a simple wave, and then you could add more complexity to it and start to see the harmonic series of a fundamental and the first or second harmonic, third harmonic, these kind of things. This is the manometric flame capsule. What the heck is that? Well, you talk into the little cone that you see there, and there is a steady flame coming through like a Bunsen burner, if you're familiar with that from your high school lab class. So there's a steady flame going, but your voice then modulates the flame so that it gets brighter and darker depending on the movement of your voice or whatever is the waveform. And then that is recorded on a piece of paper or photographic film, and you see the brightness, and you can see the next picture, I believe, shows a manometric flame. There you can see the waveform and the brightness changing with the waveform. This is you can see how desperate people were to be able to figure out these waveforms that luckily we don't have to set anything on fire to find out a waveform anymore. This was in the 1850s. This is the phonodike, which is a device that was able to project sound onto a surface. This was essentially one of the first sound waveform projectors. And you sent light through a pinhole onto a mirror, and the tiny mirror was on a tight piece of wire attached to a diaphragm. The diaphragm would cause the mirror to vibrate, and the pinhole of light would then shake up and down and create a waveform which could be traced onto a projection screen. These are again manometric flame records, and you can see the words of a poem were being I think here it is, preposterous. And you can see those waveforms. So it's pretty awesome stuff. The really big break for us comes with the oscillograph, which is now going to use electromagnetism to be able to see to be able to trace a waveform in electronic form. And this is huge. We can set things vibrating acoustically, or we can move them electromagnetically. And this, of course, is going to lead to the telephone and all of these things, microphones. And there we can see a very early laboratory at work to do this kind of sound research. You can see organ pipes there. You can see a phonodike, a phonograph, all of this great gear. These were done by Sabine. You've heard, of course, Sabine, or at least you know that Sabine is the unit of absorption that's used in acoustics, while he was the pioneer in room acoustics. And what they would do is they would put smoke into a little chamber, and they made a scale model of the room, and they would make a spark which would go through the gas and the smoke, and you could see the spark would make a vibration, and you're able to see the first direct sound wave, and then you're able to see its vibrations on the right as they came off of those surfaces. And this was the first calculations to be able to see and be able to design room acoustics with thinking about how the complex multiple wavefronts go off of these surfaces and balconies and roofs and floors. So when you look at your modern prediction program, you have really got it easy compared to these days. Moving now into the world of acoustic measurement and basically ways to measure devices. The sine wave sweep You would put that into the sound system, whether it was electronic or it was acoustic. You just ramp up the sine wave through the range of interest. You could do it manually, or you could, in the more advanced versions, you could set a timer and a rate, and that thing would swing up in frequency. The sine wave sweep is a fine tool for measuring electronic devices, but it's all this kind of changes when you move into acoustic devices. The reason being that in the world of acoustics, a key item here is how the humans perceive sound. We don't perceive sound inside of a piece of electronics, so those things like the time constants and those don't matter so much. You can characterize them more simply, but a sine wave sweep basically will give you what we call the steady state response of a system, and that's only useful in certain circumstances because the ear does not necessarily respond to just steady state stimulus. We respond to transient stimulus in a different way than things that are steady state. Think of the difference between listening to an organ and listening to a snare drum. Um, the, the organ is very long-term, steady state type of tones, and the snare drum is full of transient response. So sine wave sweep is very poor at characterizing transient response. This is an oscilloscope, which is a way that we could look at the response, and we could basically see everything that we could trace the waveform, and you could even do dual channel analysis with 2 channels of an oscilloscope and be able to discern things like polarity and relative phase. There's a plot called the Lissajous plot, which is a way to be able to look at relative phase between 2 channels. And there, yeah, you can see he's highlighting the 2 channels. It's a pretty tough way to do something with complex frequencies. So oscilloscope is useful, but limited. This is the real-time analyzer. It started in the industry as a cooperative product between Hewlett-Packard and Alltech. Alltech was a speaker manufacturer. And this product came out and it had 3rd octave, 27 bands of 3rd octave analysis and projected on that tiny little screen that you saw there. The first time I ever saw an acoustic analyzer, it was in 1986. 1976, when I visited the Grateful Dead front of house and met the engineer Dan Healy, who was tuning the system with that tool at that time. Basically, you put in pink noise, and then you looked at the energy in the bands, and then you turned the system up or down with a graphic equalizer to try to get the system to a nominal a flat response or to response of your choice. This, again, the real-time analyzer had some very, very serious limitations, such as the inability to tell time, even though it has the name time in its moniker. It doesn't know anything about phase, and it's basically a series of steady state responses. So we are going to find out that it's going to be a hard road ahead for the RTA. This is where the RTA went mainstream, device called the IVIE30. This came on like a storm in the late 70s and early 80s. Everybody had one, and you could walk around a hall with the microphone attached directly to the device. And the little guy that you see on the lower right there is the pink noise generator. So you were ready to go. You had a generator, you had an analyzer, you had a noise, and you could make it hold the response so that you could even store a response and recall it and compare one location to another. This was like the mucho awesome technology of the day. A more advanced tool that looked at amplitude and phase was the TEF analyzer. TEF stands for time, energy, frequency. It was based on the technology by Richard Heiser. Anybody knowing the history of measurement knows how important Richard Heiser was in all of this. And so this device was a sine wave sweep with a tracking filter, which allowed you then to be able to see the direct sound and screen out reflections, because you could track a filter that allowed you to see the direct sound, but by the time that a reflected sound came, which came later, your tracking filter had screened out those frequencies. So this was a way that you could see direct sound even in a room that had lots of reverberation. So kind of like if you take the RTA, which saw reverberation and just piled it on top of the direct sound, and you literally could not tell direct sound from reverberation. It was just energy. Think about it, it's just like this amount of water is in the jar. And whereas TEF could show you then what arrived first, and then screen out what arrived after. And it's very important in our perception what arrives first. The tonal envelope of the first arrival is a very critical part of our perception of the system. And think about this, if there's a 10 dB peak at 1K, all the reflections in the world aren't going to make that improve. That's going to have the sound of a system that's bright in the mid-range. And there's no amount of room that's going to make that really change that. That's a piece of signature that's there. So it's important to screen towards that. But in a fundamental way, we here at Meyer Sound, we went another direction away from the sine wave sweep of the TEF and towards the Fourier transform, the FFT, which I believe comes here. So Meyer Sound was using the FFT analyzer. They had John Meyer was using Tektronix FFTs early on, and then we had a Hewlett-Packard FFT analyzer at the company that was doing our research and development, as well as all of our quality control. And the FFT analyzer, as we're going to dig into it later, is a device that is prejudiced towards the direct sound, but not exclusive to it. So it basically is going to have the direct sound is up front, and then steadily screens in favor of that. And it's going to screen in a fashion that allows the early arrivals to screen in, whether they are low frequency arrivals or high frequency arrivals. That's going to become a key factor. So one day while I went away for a weekend, and I came home, and John Meyer had taken the analyzer to Rush and shown that he could analyze the system during the concert, and taking this thing now away from just using it on our bench and doing research and doing testing, but took it into the field, and we tuned the sound system in real time with the band playing. And this is what we call source independent measurement. And this was able to be done because there's a dual channel analyzer that compared the signal leaving the mix console to the signal arriving at the microphone. So we had the band playing, and we could do a transfer function there. We also saw that the tool for correction, which was the standard tool, was the graphic EQ, was in terrible shape. Someone's speakers are blowing out. Do you know anything about this? This is what I'm seeing on the chat.
Yeah, we hear some intermittent sounds, like swiping a keyboard or something. Let's see whether it persists. It's gone now. We're good.
Testing 1, 2. Is this better? Is this better? Yeah. I'll keep my hands off of my computer. I think maybe I was touching my computer. I'm sorry.
Okay, can happen. All good.
I will handcuff my hands. Okay. So, so anyway, we saw that the graphic equalizer was a poor tool for this work because it had fixed center frequency and fixed bandwidth. And once we could see these, the characteristics in high resolution with the FFT, we needed a parametric equalizer that had adjustable, I don't have a lav mic, so sorry. So anyway, so we were able to use the parametric EQ to make the full correction. This is a picture now of the Hewlett-Packard analyzer that we did this work on. It's called the HP 3582. It's a dual channel FFT with 128 lines of resolution. It's linear, and that's the key thing to understand about FFT analyzers and why they were not widely used in our industry or even used at all, is that they're linear. And we, of course, live in a log world in audio. And so in order to do this work, it required us to be able to have to go through a 7-step process. You could look at the whole span from 0 to 25 kilohertz, which you see right there on the screen. But that meant that the first frequency was 0 hertz and the next frequency was 200 hertz. We just skipped the subwoofers entirely. So that had very high resolution in the high end, but no resolution in the low. So what you had to do then is step the resolution down and look at only half the spectrum to 12K and half the spectrum to 5K and half the spectrum to 2.5K and on down. Until to look at the low end, we looked at just from 0 hertz to 125 hertz. Okay, so that's some pictures I'll show you now. I think we've got something, I called it the periscope, because basically we had to look at this very narrow part of the spectrum. We had to swing the periscope around in order to see it. So, and looking here at the low end, I would see just the low end, and then I would go up, and in 7 sections, it would take me to see the response. So basically it took about 4 minutes for me to see the full spectrum, what you now see in just seconds on a modern analyzer. But you could only see part of it at a time. So it looked very strange to any end user to see this response. Then, looking at on the HP, it would look like this. I would change the frequency span control and you see the same graphic that we just showed you. And basically that's what's showing up on this screen. It's 100 hertz division. Now it's 250 hertz per division. Now but it's always a linear scale, and that's what's crazy. So basically you looked at the right half of the screen all the time because the left half was too compressed to use. The type of dual channel measurements that we did, we developed a thing that's called the triple transfer function, and that's why we would do in these steps. You would first measure a system to find out what it is that we need to correct, and that was what we call the room response. So if this was the pink noise or the music that put in, this is what I would see as an electrical response taken as the signal going into the speaker system. And then from my microphone, I might see a response that looked like that. And now I can look at that difference, and that difference is what we call the speaker room transfer function. That's the thing that we have to fix. That should show up now. Do I not see that? Testing 1, 2. There we are.
Sorry.
It's okay. So that's the speaker room response, and that's what we have to correct. So what are we going to do? We're going to put that in the equalizer. We know that's in the speaker, so we're going to implement the inverse of that in the equalizer. So you'll see now we're going to change our measurement points are not across the speaker and the mic, but they're across the EQ itself. So I'm going to turn the knobs on the EQ until they make this shape, that center frequency, that bandwidth, and they're going to make that shape, and that's now the inverse transfer function. And so we've created a new problem to solve the old problem. we had a dip, we added a peak, and those are going to create a corrected result. So my mom always told me 2 wrongs don't make a right. Well, Mom, I'm sorry to argue with you, but we did it here. And so we can flatten this thing out. Now, in anything that involves a microphone, we need to add a delay line in the measurement because there's time, propagation time for the speakers to get to the microphone. But that's the basic thing. And you might look at this and go, well, why do we bother to measure the EQ? And here's what you have to remember. In 1984, nothing was digital. Okay, nothing, you didn't have digital readouts and screens that showed you what the response of your EQ was. You had the graphic EQ, which supposedly showed you the response, but that was BS. That wasn't the real response. That picture of the graphic that it made on the front panel was not what the actual measurement was. How do I know that? Because I could see it on my analyzer and compare it to what you had on the screen, and let me just tell you, they didn't match. Parametric equalizers were completely terrifying to engineers because you couldn't look at them and have any idea what was the curve that was being made. And that's why it was so important for us to measure this. And so we built our analyzer to make sure that our technique could see the actual response of the EQ. Nowadays, that's right there in your Compass software or in anybody's software. It's always showing you the response. Even the phase response is shown of any analyzer any equalizer in the DSP platforms. It's all known, but it was all a mystery at the time. Okay, so this is a really early primitive thing. This was made on a chart recorder at a concert, and we basically, this is the ultimate in cut and paste. I literally took a scissors from 7 screens and put them together and made a composite response. This was not measured at one time. It took literally to put this together. This is 1984. This was the first time we ever saw a complete frequency response at this high resolution of the FFT analyzer. And what you can see there is the top trace is the uncorrected response with the big peak and dips and things. And then you can see the response that we used with the equalizer is the very smooth trace that you see there. And then the corrected response is shown there above that. And you can see it's much flatter than the original response was. This was where we were doing that work. I can take you quickly through the ancient gear that you see there. There's, of course, the HP 3582 analyzer. There's the chart recorder that just made the picture that you saw there. The banana plugs that go into the front panel of this, they're connected to a pair of gator clips that are connected to a wire coming out of the mixing console. I do not suggest this as a interface. Kids, do not try this at home. That was the way it was there. You see an analog delay. That was homemade device. John Meyer hand built that, as well as the mic preamp. And for those who are quite young, yes, there was analog delays before there were before digital delays. And then the frequency counter, which we used that's how you use the clock to set the analog delay. Here you can see now the white graphic EQ. The white graphic EQ is a black graphic EQ, but the company is called white and they made black graphics. Don't ask me why that is. And then this is the CP10 prototype. This was hand built by yours truly. This is a hand built kind of day here. And this was the parametric EQ in a battle of the bands versus the white. And it would win the day and was used for the rest of the tour. So there's a little close-up there of our system. And this was we call it the old days. We don't call it the good old days. It's just the old days. It was literally stone knives and bear skins. But there were so many things we didn't know about that we had to find out. Like, let's just take, for example, we didn't know if what the effects of the audience would be on the transmission. That was a big, huge question. Never, no one had ever been able to measure that before with the band playing. We didn't know what would happen if it went from a quiet song to a loud song. Would the sound system's response change? We knew it would sound different, but would the response change? Would it change if we changed from the key of A to the key of C? These are all things that we now know from having measured these things and seen the response. Another big question that was beat frequencies. In case you don't know what a beat frequency, if you put together 440 hertz with 439 hertz, you'll hear a 1 hertz beat frequency. You'll hear that modulation. Anybody that ever tunes a guitar, you are listening to beats when you're listening to the two strings that you're trying to get to play the same tone. That is the beat frequencies. That's what piano tuners do as well. Well, are those something that you see in an acoustic analyzer? The answer is no. How do we know? We were able to measure those and show that you see 439 and you see 440, but 1 hertz does not show up because it's not present. It's a perceived event. It's not an acoustic. It's not there in the acoustic energy. This is now the inside of the hand-built CP10. I created those, laid out those boards myself on my back porch and wired those up, and those became the tool. The CP10 was in production for about 15 years. And its capabilities are all inside of the Galileo and the Galaxy platforms. So parametric EQ with complementary phase, so that it does the same response, whether it is a boost mode or a cut mode. And the second order phase response is the appropriate antidote for resonance-based comb filter type of responses. Wow, it's great to see. I see a lot of my friends from Japan. Hello, Kanadoi. Hello to Shoji Yuzawa and to Michitomi Yoka. Great to see you hanging out. Thank you for joining us. And Hide Nakano is here, a Japanese friend also from here in New York. So thank you all for coming. So the phase response was particularly difficult to read because it was a linear phase response on the periscope screen. And the way to see that, you had to count the number of wraparounds in the phase. So that would be 1 wraparound at, if you were on the 250 hertz band, that would be decoded to 4 milliseconds. You had to know that 4 milliseconds is the reverse or the reciprocal of 250 hertz. So that's what that means. And of course, if you go to the next span, it would make 2 wraparounds. So that's 2 milliseconds, and on it goes. Each span you go up. This is all the exact same response. It just looks different depending on what span you're looking at. It's 2.2 milliseconds per wrap, but every one of those is a picture of 4 milliseconds. And I'll tell you what made it really challenging in those days. The speakers were, shall we say, not at the current standards. We literally would find like a speaker at 8 kilohertz, you would find it, and then its response at 1 kilohertz might be in 1 or several milliseconds away, and then a whole another set of milliseconds away to find the low mids. So it was a challenging time because a speaker was a moving target over phase over time. In 1984, we went to the AES and we presented our findings that we could equalize systems using voice or music as the source. We were very excited about this, and we knew that we were pioneering something. We've basically gotten into a region that no one had ever seen before, and we're able to prove that we could visualize this response. Um, and so we actually did a live demonstration at this workshop, and I did a tuning in real time, showing we created a reflection, and then we equalized that out, and we showed that we could do that in real time. And in the paper, it shows a version that we did here in the room, where you can see a peak and a dip in the top there, and the uppermost screens are a peak and a dip that were created by a piece of plywood we put next to a speaker. And then we applied this filter, which had the inverse amplitude and inverse phase. And on the bottom two traces, you can see an improved amplitude and improved phase response. And if we wanted to throw more filters at it, we could have done even more work on it, but that's the level that we took it to. And so you can imagine the AES was very excited about this, and this is how they answered it. And the paper was never printed. I won't get into the politics of how that happened, but suffice to say that there was some people that didn't like the fact that we stated that you could equalize a reflection after it had left the speaker, and insisted that we remove that language. We did not remove that language, and we continue on our journey, and there we are. In 1984, a typical small system could be console, left EQ, right EQ, and a left and right speaker. A big system was essentially the same thing with just a whole lot of speakers, but still the architecture of the system was just a simple EQ left and an EQ right. There's none of the kind of complexity that we think of now. You look at this system now and you immediately are thinking, okay, there's a separate level, delay, and EQ for at least 5 sections that you can see there. But no, that was all done on a single EQ with no delay. And that's the state of things. So it's important to understand that at that time, the only function that we were doing was equalization. And equalization now got us into a kind of a tug of war with front of house engineer for whose EQ is best. Is it the EQ that the science guy says from his analyzer, or is it the EQ that I say from my ear? And if it's just a fight over EQ, frankly, we have no reason for the analyzer. If all you're going to do is EQ it for how you like it at front of house, please don't bring an analyzer and waste our time, because there's no function for it. Just tune it till you like it. There's no wrong answer, and there's no right answer. There's what you like. The real function of this became when we started to break the system into subsections and emphasize what we call now system optimization. And system optimization is all about making the system so that it has uniform response over the room. In order to do that work, we needed to do much more than just analyze the system at a single point, in real time. We needed to be able to store the response at one location and compare it to another. And to do that, we needed a computer to be able to store and recall responses. And that brings us to this modern, super hot, high-level computer of 1984 that was the HP 87 that ran on HP Basic. It's pretty laughable when you look at that, but that was the tool of the day. And this allowed us to remote control the FFT analyzer and to be able to take traces and take them off of there and put them back. And that allowed us to be able to see multiple locations, to be able to look at and store. I can move the mic to 8 different locations and store those and recall those and compare those. And that's, of course, that's the modern way that we do system optimization now. It's not about any one location. It's about making everything sound uniform over the space. I did the programming for this myself. Thorny was a big mentor for me on this. But essentially, I learned how to program in BASIC because there wasn't anybody else that was going to do it. This was, and it was, as Thorny called it, spaghetti code. But it was what we did in order to learn how to do this, and then this would become evolve into the next level. 1986, we took the product and we took a prototype and we showed it at the LA convention and showed them that we were ready to make this into a system that you could take on tour and go and tune your sound systems. And we called it SimCAD. And pretty bad choice of names considering SIM would eventually be overrun by the SIM cards in your phones, and CAD would be overrun by computer-aided drafting. So we kind of hit the jackpot there with SimCAD. But there you go. The product never was made in that form. It was made in the form that you're going to see next. It was what we call Sim System 1 now, although the software did call itself SimCAD. And that's still the Hewlett-Packard analyzer, but we have a multi-channel interface, a next generation of Hewlett-Packard, which was faster and had a whole stinking megabyte of RAM. And it ran on this 8-channel switcher with a digital delay line. That's what DDL means, so that we could basically now go from what we call branches, a microphone and a set of EQs, and with repatching once and without moving, you could compare 8 different equalizers and 8 different microphones and measure them all one after the other. And this was a system that was ready for any system of the type of complexity of the day. You could even expand it to 16 or to 24 if you had the money and the time and you were willing to carry that amount of weight. It was, as you can see, very heavy, 300 kilos or 600 pounds. It was a mother. There it is at the Montreux Jazz Festival, and doing monitoring the response night after night at the Montreux Jazz Festival. This is the plasma screen of that guy. It was a good, it kept you good and warm, and notoriously unreliable. Oh, that integral computer. The number of heartbeats I lost over the reliability of that device, I just can't tell you. I kept my Torx wrench with me at all times, ready to open that thing up. Oh, I can't tell you.
And was this also the display where you did your coding?
Yes.
Wow. 5,500 lines.
Yes, sir. This is the Jubilee Auditorium in Calgary. These are the people that bought the system that we demoed at AES, and that forced us to actually build the thing. And that's why you have a Sim 1. You can thank Rick Packer on the left. That's why this thing ever happened. Here I am doing my thing. You know, the little computer was just for storing and recalling traces and managing what you actually were going to send to the computer to send to the analyzer. But the analyzer was all the analysis was still done on this Hewlett Packard, and it was still the linear display, and it literally was for those 3 transfer functions of 7 spans each, it was 21 measurements in order to do a full characterization of a system. So we knew that this could not be the long-term solution, and we'd been measuring systems for 4 years now in 1988, and we went to Hewlett-Packard. We respected that company. We used their test equipment to, we're getting editing here. And so we used their gear, and we told them, and we gave them the full recipe for what this thing had to be. We needed a log frequency axis. We needed an impulse response so that we could tell time with an impulse instead of decoding the phase. We needed the 3 live transfer functions. We needed to be able to remote control our switchers to get access to all of our channels. And we needed to be able to store a comprehensive library of data. That was the basic criteria. We gave them that entire recipe set, and this was their answer. Seriously. Their answer was to go and for us to buy 21 of their analyzers, which were $12,000 each. And it would have weighed 2,000 pounds to take this. You would need your own dedicated truck for this. So we said, thank you, Hewlett-Packard, goodbye. And we decided at that time we had to build it ourselves because no one was going to build it. And that's why SIM2 came to pass. And there is the SIM2. The SIM2 was all of the things that I just described, and a single response was viewable now. So this was all the switches that you saw before condensed down to a single device. What used to be 12 rack spaces was down to 2. People still say that's huge. Well, it was small at the time, but that could do 8 channels of EQ, 8 channels of microphones, and super fast 33 megahertz PC, and the delay line built inside. So it's ready to go. And now you're actually controlling the system and viewing the data in the same place. And you could store 24 sets of data, huge amount of data. So you can move the mic around and really see now what things were different. You could bring up last night's data and compare it to tonight's data. You had all sorts of capabilities that we knew we needed, but had never had a chance to have.
So Bob, how did you solve the linear frequency scale?
The linear frequency scale is solved by what's called the constant Q transform, and it's by taking those same FFTs that you had before, but essentially you're going to just use part of them. We would do 48 points per octave, and then we would chop off and just use the top octave of each and do another one, and then splice it together into one video. So the video representation that you see is the product of the periscope. It's just that we've spliced them together so nicely you don't notice. So if you go forward, you can see here, these are, what here is linear display on a linear frequency axis. And then you see long linear display on a log frequency axis. So it's not enough just to do a log frequency axis, because if you just do a log frequency axis, you end up with a bazillion points in the high end and terrible coarse resolution in the lows. And if you do the linear, as you can see, you have constant resolution, but look at where 1K is. 1K is the second, 1K is the second line in that screen on the left, and is the middle of the screen on the right. It's just, right? So your subwoofers are just a dot in this, and okay? So what we did instead was called the constant Q transform, And that's in the next slide. And that is that we would take a 5 millisecond record for the highest frequencies and then double the time record for each octave going down until we were at 640 milliseconds in order to get down with good enough resolution in the low frequencies. Yes, we could take in 5 seconds to get 48 points down at 16 hertz, but no, nobody has time for that. We have a show tonight. So 640 milliseconds was what we felt was the longest that we could go and get a good enough to get 16 averages and be able to get us a good resolution. So that allowed you 6 points per octave below 20, 12 points per octave from 20 to 40, and 24 points per octave from 40 to 80. Pretty good from there. So in
Now,
sim, go ahead.
no. Finish, please. By all means, finish your story. I had just one question to follow up, but.
In sim 2, we were doing 24 points per octave. By sim 3, we moved up to 48 points per octave. That's why both of those are shown on this picture.
So I wanted to ask, correct me if I'm wrong, but having multiple time records also allows you to preserve useful reverberation in a frequency-dependent fashion while rejecting detrimental reverberation. Correct?
That's what it's about. Yes. So if you think about it as that at 10 kilohertz, a 1 millisecond is still an early reflection, makes comb filtering at 1/10 of an octave, but 50 milliseconds is very late. It makes a 5/100th of an octave comb filtering. But 50 milliseconds is still very early down at 30 hertz. It's only 1.5 cycles. So that's going to create 2/3 or about 2/3 of an octave comb filtering. So it's still very, very much in the tonal window. So we slide that thing down to keep you in the listening in the tonal type of window where EQ is still a favorable option.
Correct. So we prepared this, and that basically brings us to the end of this part. So how does history evolve from here on? Because Sim 2 basically set the trend. Now there's this turnkey solution, which contains all bits and pieces in one package. And how does history run its course from here on?
Well, where it runs its course is that once you reach Sim 2, you have evolved the tool that is everybody's using now. Everybody's, all of the modern analyzers, whether it's Sim 3 or whether it's Smart or any of these other tools, are basically using that technology. You get a transfer function magnitude, you get transfer function phase, you get coherence, you get an impulse response, and you maybe do other sexy things from there, but those are the essential things that you need to do system optimization. And from there, system optimization then evolved into a very, we got our experience to be able to evolve that to a mature methodology. System optimization evolved beyond just a tug of war over the house EQ and which tone is best. It evolved into be able to determine whether speakers are aimed right, whether speakers are splayed right, whether speakers are spaced correctly, whether a reflective surface is causing you trouble, whether there's a polarity reversal in the system. All of these things can now be found by the analysis of those amplitude, phase, coherence, and impulse response. And that allowed us then to advance these techniques to the levels that we have them today. Everybody knows now how to tell if the speaker is aimed correctly. You place if you want to see the vertical, you place a mic at the top and place a mic at the bottom. And you're going to look at those two things and work them to where the response at the top of the bottom is equal. Then you know you've aimed it correctly. Another question, of course, is whether or not that's a good enough speaker, whether it's wide enough. Well, that is another question that needs to be answered, but that's answered by comparing that to the response on axis. So all of these things now, we have the multi-channel capability to average or to look at multiple microphones at once. We can average responses together. We can recall and compare traces upstairs in the balcony, downstairs on the floor, room empty, room full, um, change display, and you'll see these things change. So this is tremendous advancements, and of course the tools are getting faster. By getting faster, it means we can do more operations in a shorter amount of time. Why do we need a shorter amount of time? Because everybody gives us shorter amount of time. That's the nature of our business. If you used to get an hour to do something, well, now video has taken half that time, so you get a half an hour to do it. So, and we know video, we can't be doing sound while video is doing their thing. I mean, that would ruin the video. I mean, let's get serious. We've lost your sound, Merlin.
That happens. Unfortunately, that happens rather often. But I was about to say, yes, seeing what kind of equipment was available to you at the time and what you had to work with is very humbling, for lack of a better description. Because, with today's modern computers, it's all of that equipment that we saw, now fits into your backpack. So, yeah.
And so much of the system is now already pre-optimized. The modern systems are so much, there's so much correction. They've got their crossovers are already done. We don't have to construct crossovers in the field. We have phase-aligned speakers. We have such superior tools that it allows us to move really to the optimization and spend less time actually making a speaker in the field. We really have tremendous, and we've used these same tools, these same analysis tools are used to manufacture better speakers and to research and development of better speakers. But it takes a big load off us on the field. We literally would have to, speakers were so phase incompatible in the old days that it was just tremendously difficult to do this work, and so much verification when you have all these different connections that could be wrong between amplifiers and banana plugs swapped and all sorts of stuff.
Right, which is inconvenient in an industry where there's one constant, which is that there's always too little time.
Exactly.
So, how do you feel about opening up for Q&A?
Oh, happy to do that.
Okay, well, that means that those that want to ask Bob a question, please make use of the chat to pose your question, and then I'm sure that Bob will try his best will try to answer your question to the best of his abilities. So Alex is asking, which was to be expected, are there any plans for Sim 4?
Sim 4 is an active project, but it will not be. It is not going to be on your shelf tomorrow. I can promise you that.
Right, agreed. Okay, any other questions regarding today's topic, the evolution of system optimization? So Joel Brito is wondering, what did you use for the HP? Did you actually program it for FFT?
No, the HP87 did the following functions. It could take a trace off of the FFT analyzer and hold it in memory, and then it could send that trace back. So you could do a before and after, for example, a room empty, and store that into the HP87, and then when the show started, I could bring that up and compare that to what I'm seeing now with the band playing in the room full. And then it also would select what anything that's going on the analyzer. It would select what microphone I would measure, what EQ I was measuring across. It would set the delay line for the to compensate for the propagation time. So everything there was done, but the actual calculation was done by the FFT analyzer. We don't move and do, we don't move into doing the FSTs ourselves until Sim 2.
Now, Bob, following up on that question, was the HP analyzer, was that an analog analyzer or was it already a digital analyzer?
It was loaded with diode logic and transistor logic. It had tons of analog parts in it, but I do believe it was a digital calculation. But
Yeah, because
digital in an extremely in a first generation type of form.
right, because as you're saying this, I'm wondering that in order to get the information into the computer, it has to somehow be digitized.
It requires a sampling. You know, you have to do it you have to bring it down to an A to D conversion. Yes.
Right.
You're doing the time decimation to get that waveform.
Right. Okay. Does anyone else have a question for Bob at this point? So Jeff Vanderkoy is wondering, what do you see in the future of system optimization? Both is technology and the art. The latter part is not entirely clear to me, but what are your thoughts on the future of system optimization?
What I see is that the systems I see it like a loop, that the optimization work that we did in the field, where I talk about how the speakers themselves were so required so much work in the field, well, that then got put into the speakers. So the things that we kept doing to speakers then got built into speakers. And so then it was already done and we were able to move forward. And I see that is still an ongoing process. We see the kind of operations that we perform over and over going into these things, going into the tools in the form of evolved presets and these things. And even to some extent, you can see more intelligence that's looking towards reading the traces, averaging the traces, and possibly then making suggestions of responses. I think that I've spent my life looking at traces, and I've seen a lot of traces. So I have a collective, 35 years of experience when I see a trace come up on the screen. And I think that we're going to see our analyzers get this experience can be built into the analyzers to make the kind of decisions that we're making with our experienced brains.
So you said that on one end, part of the heavy lifting is being moved out of the calibration process downstream into the loudspeaker. But at the same time, is it safe to say that loudspeaker systems overall became more complex, so that at the end of the day, in terms of workload, it still leverages one against the other?
Exactly. So, I always seen that as a loop. If you look at a modern Broadway a musical theater production, they've got so much complexity, so many channels. Well, they can feel bold and safe managing that kind of complexity because they know that they can get the system optimized so that you can space map a signal around the room, and it doesn't go and sound completely different when it moves into the sides than when it goes to the rear. That's can only happen if you've got well optimized designs and you've implemented the optimization in the field. So I think that you look at the move toward immersive audio that's moving through the live sound concert world, and that's going to become more manageable because the systems are, because you've optimized those systems. If those systems are not optimized, good luck, baby. You know, you've just made the system more complex. Uh, you know, you want to talk tough, you better be able to handle it.
Right. So Mikhail is asking on the chat, can you compare the precision of old sims and nowadays analyzers? And he means how detailed was it? Never mind how quick it was, but how detailed was it by comparison?
The resolution of sim 3 was 24 points per octave, and that is a very standard resolution. Sim 3 went to 48 points per octave, and I believe that that Smart is around that same level. Smart does a little bit. They've got some. You could maybe speak more to the exact. It's got some elongated octave,
Yeah,
more than an octave
depends on
span.
the sample rate,
Um,
which time constants are being used, but it's very much in line with what we've been doing.
it's from a resolution standpoint, Sim 3 is 100% full resolution. There's really no need for any resolution beyond 48 points per octave because you simply don't have any work to do beyond that. You really do most of your work at at sixth octave. Is it pretty much the narrowest kind of work that you should be doing, and 24th octave gives you an oversampling of 4 to 1, and 48 gives you an oversampling of 8 to 1 over that resolution. Why do you want to oversample? Well, it's really great to be able to see something in more resolution than you're going to act on it. So that then you can more carefully verify its center frequency, its bandwidth, and its magnitude. So
Right.
I always look at things in the maximum resolution. I haven't smoothed a trace in like 25 years. I look at things down and dirty in the full resolution.
Same here, but I think to the to the to the people that are new to this field, that if you look at high resolution data, that very often it can end up being serrated, it can be jagged due to
Yeah.
a hostile environment, which is of course, and then it's very compelling to consider smoothing to make sense out of the madness. But I think
Yeah.
it's also important to point out that high granular data is way too fine for the hearing sense to resolve. So having that high resolution is for me is always a double-edged sword, because like you, I look at it always in high resolution, resisting the temptation to smooth. But that's because with practice makes perfect. But especially in the hands of people that are new to this, smoothing is of course very compelling when you're dealing with high resolution data.
Yeah. The thing to think about is that we do perceive all those super fine things. We just don't perceive them in the tonal sense. We don't say,
Right.
oh, I hear a peak at 12,296 hertz and a dip at 12,299. No, that's not the way it works.
No.
What you hear is those super grainy parts are heard as reverberation, and it makes a difference. There's a difference between a trace that is smooth because it's smooth and one that's smooth because you've done electronic smoothing on it. And that difference is the sense of reverberation. I want to know that trace that's getting hacked with a machete, I want to know that because I want to look at possible solutions, like seeing if there's some absorption, seeing if I can do a different splay angle, or seeing if I can aim it a little differently. There's other possible things that might be indicated, but no, I'm not going to put a filter at 12,694.
Right. So we have a French attendee, Flo, who is wondering whether this is my interpretation because he is not an English speaking person, but he's wondering whether the aiming and displaying nowadays is done primarily within the simulation software, whereas the optimization is the remaining 20% on the spot. Is there a change in the balance between the design work and the measurement work on site? Has that changed? Has that shifted in some way?
Well, in the time of 1984, when my personal story begins with this, there's of course no prediction at all. So everything that we're doing, I mean, literally, we would sit there with a protractor and these kind of tools. But as the as the prediction stuff has evolved, it's in a loop. I look at predictions and then I look at, then I implement that in the field and I verify that that prediction is correct. And had one, did a recent job. I actually had to do a job where I tuned a system in Virginia from my home because I was not able to get to the site because of coronavirus. Okay, so this was a case where I'm really dependent on the prediction, and the prediction was wrong, not because the prediction software was wrong, but because the accuracy of the rendering of the room or the placement of the speaker, whatever was not accurate, so that the field had to finally in the end say, no, that thing needs to aim and we need to redo, pull the cluster down and redo the display angles for it then to work right. I think that as these things evolve, we're getting a lot of our work done in prediction. That is for absolute sure.
Right.
Whether that's 80 or 20, I don't know. But at the end of the day, it has to be verified and proven in the field.
Yes, and there was one particular verb that struck a nerve with me, which is that you use the verb validation. I feel like you that the analyzer is first and foremost a validation tool, not an exploratory tool. It's not like, okay, let's see how to aim the speaker, rather than let's see if we aim the speaker properly. Let's validate whether we did our homework.
Yeah. And we always, you've got to start with a plan. You don't want to go and start just bringing the speakers in and start making it up by measuring things. Nobody's got time for that. So you got to give your best shot. But at the end of the day, you're going to find out what is really happening. You've got to be ready for Plan B. I really, when I do a tuning, try to have everybody ready to be able to rework angles or touch up aims. And I always work to make sure that the biggest parts get sussed out first. The part that's going to potentially require 2 hours to make an angle change, I go right to that guy. And then if that's going to take 2 hours, then I'll start working on the front fills while that is going down, this kind of thing.
Right.
But I can tell you that the map prediction program constantly amazes me at its accuracy, because it's got completely totally accurate phase response and characterizations of the speaker, and we will sit there. I have had my jaw drop as I've watched I've looked at the virtual sim picture on map and said, this is what it's supposed to look like. And then I put the mic there and holy God, it is an absolute match. And I'm just stunned and just go, whoa, baby, that is science.
It's good for confidence.
Oh, it's amazing.
So does anyone else have any more questions for Bob? So Daniel's wondering, like airplanes, systems nowadays are becoming more and more autopiloted. Would this make the optimization work less important?
Well, here's what I would say. When it comes to an airplane, whether or not the pilot is flying it or the wire and computer are flying it, it's still really important that the plane be flown correctly. So I would say optimization of that plane's route is very important. And I'm going to just say that optimization is still really important. What it just means is that the parts of it may, it shares that it takes mundane tasks may become more able to be accomplished by automation. And then you're still overlooking to see that it makes sense. And I can be fooled. I'm a computer. I can be fooled. And a computer that's a computer can be fooled. At the end of the day, you gotta sometimes look at that and say, hey, wait a minute, is the meter wrong? Are we really losing altitude, or is that altimeter lost its way?
Right, which is if you would allow me to add, is this is also the thing that I notice is that you can ask a computer to look for a needle in a haystack and it will find it. But especially now with the rising popularity of AI and such, it's my understanding that something that computers can do not very well is generalize. And from personal experience, I know that I generalize a lot. Whenever you assess a phase trace which has been compromised due to room interaction, we generalize because we have the experience to make those generalizations. And this is something where I'm very skeptical as to whether this can be solved by a computer, the generalizations that we make on a daily basis.
And you and I have had this discussion before, but my approach is that before that trace comes on the screen, I place my mic and I draw in my head what I'm supposed to see. I have expectations. Because I can look and I see where the speakers are, what the room is. I've taken in all of the context clues that tell me what this thing should be. And when that comes up and is not what it should be, it's like, oh, I don't act on it just because it does. My favorite saying is, if it's too good to be true, it's BS. Okay, so don't go and say, wow, this looks really good, so I don't need to do anything. Well, it turns out the speaker is actually aimed at the ceiling, or or a different speaker is on. That's why you're getting this response, or there's all sorts of stupidity that can happen. Believe me, I have done more stupid to any sound system than anybody perhaps on this call. Why? Because I've been learning for long.
So I think we have time for one more question, and then we're into this 1.5 hours, which is McCall asking, I know it's a complex question, but are you a fan of the digital domain or old-fashioned analog world? Wow.
I can tell you that I am a fan of things that perform better. Of course, I have a very, very emotional attachment to the CP10. I mean, that is my child. And I'll always remember the day where we went to Wicked in New York. In New York also, but also in London, where I worked with Paul Garrity, who I see here on the call. Hi, Paul. And we, with Tony Miola, we took out the CP10s that had done 11 years of service there and replaced them with the Galileos. And there's no doubt those things outperformed. The noise floor went way down, the clarity went way up, all those things. Oh, that's great, Marcia's there too. So, because she worked on Wicked. So this is, these things outperform. And I don't have any romance with analog. I don't listen to vinyl. I have no romance over these things. I even, I have a guitar amplifier, but this is the guy that I actually use.
I was thinking of bringing it up, and I thought, okay. Well, he has an analog guitar, but he has a digital pedal board, and I was like,
exactly. this this part's this part's analog.
Right. Awesome. Okay. Well, I feel that that made for one hell of a super interesting webinar where you took us on a very exciting journey, talking about the evolution of system optimization. I can only say, thank you so much to you as well, to Meyer Sound, for exploring this field, making it possible. Um, Kudos to all of you. Hats off. And that means that thank you, Bob. Thank you for doing this as always.
Thank you.
Looking forward to many more of these sessions. And that means that a recording of today's webinar, as always, can be found within the next couple of hours or so on our Meyer Sound Thinking Sound YouTube channel. Be sure to visit that YouTube channel if you want to know more about what Bob was talking about regarding Tony Miola and Wicked and Kai Arada and all those people involved in productions like those. Be sure to watch Bob's other webinars that you can find there on Theater Sound and such. And what else do we have in mind for the remainder of the week? Well, Friday, we're going to have a case study of Montreux Jazz Festival. We have two guest lectures, which is José Godin, who is a known entity at Montreux Jazz, as well as Amanda Davis, front of house engineer freelance. Both of them will be joining us, and we'll talk about Montreux Jazz this Friday at great length. And myself will be doing a live rerun next Monday due to popular demand. We're doing these live reruns only on Mondays. We've done dozens of webinars in the past couple of months, and people have been asking, can you do them again? Can you conduct them again? So this Monday, I will be conducting the Autosplay webinar. And what else is going to happen next week? Well, for that, you'll have to stay tuned. Consider joining the Meyer Sound User Community Facebook group. That's one of the first channels where we will bring you up to date regarding future webinars. Other than that, thank you, Bob. And to those that joined us today, please stay safe, please stay healthy, and best to you and your loved ones. Bye-bye.
Thanks.